I'm Dr. Sreekanth, Professor, Department of Data Science, Institute of Aeronautical Engineering. In this session, we are going to continue the predicate calculus. Now we are going to give a sentence. Now we are going to try to convert into a symbolic form. See, last class we know what is a predicate point function and what is a generalized predicate and a predicate point function, and how we are going to combine the two predicate statement functions and compound predicate statements we are going to get. So some of the sentences we are going to convert into a symbolic form. Now let us consider one more example. So we are going to convert into a symbolic form. So for that, so it is given, translate the following into symbolic form. One is, all men are mortal. All men are mortal. Socrates is a man. So using this, we have to prove this, Socrates is mortal. So here, all men are mortal. Let us, for this, m of x. See, this is a predicate, x is a man, and h of x is mortal. X is a mortal. Then if we are going to take m of x and h of x is man is mortal. Man is mortal. So here the quantifier we are going to adopt, we are going to keep for every x, means we are going to take all men are mortal. All men are mortal. Now let us consider S is a Socrates. S is the object here. S is a Socrates we are taking. Then m of s is nothing but Socrates is a man. So now h of s is Socrates is a mortal. So here let us take m of s and h of s. That is, Socrates is a man and he is a mortal. He is a mortal. So this is the symbolic form. So first of all, we are going to write what is the symbolic form for the all men are mortal. All men are mortal. Then after that, Socrates is a man. So after that, Socrates is mortal. Socrates is mortal. So we are going to get the symbolic form for this. Symbolic form for this. So Socrates is mortal. Before that, all men are mortal. So we are taking x is a man. M of x is a man. H of x is another predicate. X is mortal. Then if you are going to combine these two by using AND operation, then m of x and h of x is nothing but man is mortal. Then we are going to keep the quantifier for every x, that is nothing but all men are mortal. All men are mortal. So now for this, now Socrates is a man. For that, m is a man. Then m of s, Socrates is a man, and h of s is nothing but a Socrates is mortal. Then we are taking m of s and h of s is nothing but a Socrates is a man and Socrates is mortal. Now let us consider the free and bound variable. So here let us, for every x, p of x, if p of x, then there exists x, p of x or q of y, be a predicate statement formula. In this predicate statement formula, let us consider this is the predicate statement formula. In this, we are going to consider for every x p of x, there exists p of x or q of y. These are all called parts of formula, predicate statement formula, parts of predicate statement formulas. So in these parts, the formula, so here for every x p of x or there exists x p of x is called x bound part formula. X bound part formulas. So x bound part formula. See here, bound variable means any occurrence of x in an x bound part of the formula is called a variable. Is called a variable or bound variable. Bound variable means any occurrence of x in an x bound part of the formula is called a variable. So now another definition, free variable. Any variable that is not a bound variable is called a free variable. Is called a free variable. And next another one is another definition, scope and scope of the quantifier. Part of the formula immediately followed the quantifier, followed the quantifier is called scope of quantifier. Part of the formula immediately followed by the quantifier is called a scope of quantifier. So let us consider, I am taking, this is the formula. Example, this is the x bound formula. Here the quantifier x is a bound variable. Then it is immediately followed by the predicate p of x. So p of x is nothing but the scope of the quantifier. P of x is nothing but the scope of the quantifier. So here bound variable, free variable, scope of the quantifier. So bound variable means any occurrence of x in an x bound part of the formula is called a variable or bound variable. Free variable means any variable that is not a bound variable is known as a free variable. Scope of the quantifier means part of the formula immediately following the quantifier is called the scope of the quantifier. So now let us consider the another one. So let us consider p of x is x is a person. P of x is x is a person, and f of x comma y is x is the father of y, and m of x comma y is x is the mother of y. Symbolize that x is the father of the mother of y. We are going to write the symbolic form of the statement. X is the father of the mother of y. So let us consider, we are going to take one variable. Let us consider that as z variable, such that z is the mother of y. So we are taking z is the mother of y. So now m of z comma y, z is the mother of y, and f of x comma z is nothing but x is the father of z. So now f of x comma z and m of z comma y is nothing but x is the father of z and z is the mother of y. X is the father of z and z is the mother of y. If such person exists, we are going to take it as p of x and f of x comma z and m of z comma y. So that is a p is nothing but x is a person. See, if that such person is known as exists, then I am taking x is a person. So now we are going to take there exist. There exist means it is a few only, or one only, or some only. So whatever, not for all. So we are taking this as there exists x, quantifier we are going to implement, and p of x, the same thing we are going to written here. The same thing, which is nothing but x is the father of mother of y. X is the father of mother of y. Of course, x is the father of z and z is the mother of y. So the intermediate variable, if you are going to remove, then x is the father of the mother of y. So like this, we have to symbolize the statement into the symbolic form. Next, another one. Symbolize work is worship. Let us consider one predicate. W of x is predicate point function. So it is x is work. So next, another one is z of x is worship. So now just combining, so w of x and z of x is work and x is worship. So just we are going to keep for every quantifier. So for all x, work is worship. So this is true for all. So now generalization of this is work is worship. So first we are going to take a predicate point function w of x and another predicate point function z of x, and we are going to combine. So we are going to get for every x, w of x and z of x, which is for all x, work is worship, or x is work and x is worship. This is true for all values of x. So generalization of this is work is worship. Now, let us consider the second one is everybody loves a patriot. Everybody loves a patriot. So here we are just taking everybody loves. So first one is here it is a person. Every person loves a patriot. So let us take one is x is a person. Now x is a patriot, q of x, and then we are going to combine these two. So L is y comma x is y loves x. Y loves x. We are going to consider a predicate point function of x variable, and next q of x, and is also a predicate function, and another one is L of y comma x. So this is also another one. So just we are going to take if q of x, then L of y comma x can be written as if x is a patriot, then y loves x. If x is a patriot, then y loves x. Assume that there is a person exists. That person we are taking it as p of x. So p of x, and we are taking the same entire as it is. So that is x is a person, and if x is a patriot, then y loves x. So this is we are going to say for all. So for that reason, we just keep one quantifier. This is for every y, p of x and q of, and if q of x, then L of y comma x. That is nothing but everybody loves patriot. So this is the how the sentences can be converted into the symbolic form by using predicates. Now let us consider the other one. See, let for every x, q of x comma y be x bound part of the formula. So here x is called a bound variable and y is called a free variable. See here, let us consider we are taking, see here this is a quantifier will be there. Quantifier we are mentioned for the variable x. So the variable we are calling it as a bound variable, and where the quantifier is not defined for any variable, such variable we can call it as a free variable. And of course q of x comma y is the scope of this. So let us another one is for every x, if p of x, then q of x be a statement formula. Here x is the bound variable, and next followed by this one. This is the scope of x, and this is the same one earlier. Whatever the what is the scope of scope, and what is the bound variable. So here also for every x will be there, for there exists y will be there. So for this x is a bound variable and y is also a bound variable. Then the scope is we are going to take it as this is the scope of x, and of course this is we are going to consider scope of y. Now the continuation of that earlier, just symbolize all cats are animals. So for that, let us take one predicate, that is x is a cat, and another predicate x is an animal. Predicate point function x is an animal. So if x is a cat, then x is an animal. So if then principle, if x is a cat, then x is an animal. We are going to write a cat is an animal. If x is a cat, then it is an animal. It is an animal. So just we are going to keep for every x means that all cats, all cats are animal. All x, if x is a cat, then x is an animal. So just simply we are going to remove the variable, then we are going to get write all the cats are animals. That the symbolic form is this. That the symbolic form is this. Now let us consider what is the universe of discourse. What is the universe of discourse? The domain of object variable. The domain of object variable is called universe of discourse. Universe of discourse. So here, what is the domain of the object variable? So here, whatever the objects, so here x is a variable. It is in general we are taking the range or the set. If you are going to consider the entire set, we are going to call it as a universe of discourse. Universe of discourse. Let us consider one example for this. Let s of x is x is a student, got first class. S of x is a student, got first class. And next, a, for every x, s of x, all students got first class. Then the meaning of this is there exists x, s of x is some students got first class. Some students got first class. So just we are going to explain the quantifiers by using the quantifiers, and here we are saying all and here we are saying some. Okay, now let us consider x is a member in this set. So x belongs to Ashok, Balaji and Suma. So there are three objects will be there. X is any one if you are going to consider. That means for all x, s of x means Ashok and a domain. Whatever the object's domain will be there. That is Ashok, Balaji, Suma got first class. Got first class. So here the domain, whatever the domain we are going to consider, that is called universe of discourse. That is called universe of discourse. So here x is Ashok, Balaji and Suma. So this is called a universe of discourse. Universe of discourse. So for every x, s of x is true, then 3 got first class. All the 3 got first class. There exists means at least one Ashoka or Balaji or Suma got first class. Got first class. So here the meaning there exists means all the members in the domain, all the members in the set which are got first class. There exists means some anyone. Now let us consider the another one. So here a of x is less than 10. Find the truth values of this and this. Find the truth values of these two. And the universe of discourse is given. For this universe of discourse, what is the truth values of these two? And for this universe of discourse, what are the truth values of the 1 and 2? And for this, what are the truth values of 1 and 2? So here, so let us consider x, b, and any element if I am going to consider from this set. So a of x, let us say the first element, minus 5. So a of x is less than 10. So minus 5 is less than 10, which is true. Minus 3 is less than 10, which is true. Minus 2 is less than 10, which is true. 0 is less than, 1 is less than. Like that, each and every element in the universe of discourse which satisfies, which is less than 10, which is less than 10. So we are going to say that for all values of x, a of x, that means all values of x are less than 10, The truth value is true. The truth value is true for this. And the second one, there exists a x a of x. There exists a of x. That is nothing but for some values. All the values, if it is true, for some values also it is true. So for some values also it is. So this is some values means at least one. At least one. This is true for all the values. So whenever for all it is true, automatically it is true for there exist also. There exist also. Let us consider the second B, universe of discourse. Universe of discourse. See, once again, a of x is satisfied or not. So here, this is, if I am going to consider these two are not less than 10. These two are not less than 10. That means for all x, a of x is not correct. For all x, a of x. That means each and every value of x in the universe of discourse will not satisfy a of x. So the truth value of this is false. So here, the second one is, some of the values are satisfying. Up to here, satisfying a of x. That means at least one value is satisfying. So for that, there exists x, a of x, which is true. From the first one, all the values of the universe of discourse are not satisfied. So we are taking it as false. Some of the, or at least one satisfies the condition. So we are saying it is the truth value is true. Now let us take the third one. And here also, see here, no value is less than 10. No value is less than 10. Then for all values of x, a of x is false. For all values of a of x is false. The truth value is a of x false. And at least one of the variable is not satisfied. One of the variable is not satisfied. So this is also true. This is also false. This is also false. So here, none of the element in the universe of discourse satisfies a of x. So we can say that truth value for all values of x, a of x is false, and there exists x, a of x is also false. A of x is also false. Now let us consider the another problem. In the following predicate statement functions, identify bound and free variables and scope of the quantified. So this is the continuation of the earlier one. So here we are going to identify what are the free variables and what are the bounded variables and what are the scope of the quantified. So the first one is, so this is if you are going to consider. So here for every x, there is a quantifier for the variable x. So we can take it as x is the bound variable. X is the bound variable. Whereas see here, x is the bound variable and here also x is the bound variable. X is the bound variable. And next, the scope of the first quantifier is this is. That means the quantifier is followed. The predicate which is followed by the quantifier is nothing but the scope of the first quantifier x. And the next quantifier, so this is. So the next quantifier is this. So the second scope is p of x is scope of the second quantifier. And for the second problem, for the second example, so here for all x, p of x, and there exists x, q of x, and for all x, p of x, biconditional r of x. So here, wherever the quantifiers will be there, see these are all bounded. These are all bounded variables. So which we represent with the red color is represented as the bound variable. And of course, the first scope of first quantifier is p of x. So the first one is p of x and there exists q of x. Is the first scope of the first quantifier. And next second one is there exists the q of x is the second quantifier x. Then another one is p of x is the third quantifier of x. Third quantifier of x. And like that, the third one, if you are going to consider, same, these are the bound variable is x. And next, first one is a of x to b of x, and r of x is the scope of the first quantifier. And next, another one is the second quantifier is q of x, not q of x. Here there is no q of x. So here it is r of x comma y. R of x comma y is the third quantifier. Third is will be given as a third quantifier of x. And of course, there is no q of x, and we are going to consider this is the here the y is the free variable. Y is not quantifying. We are not mentioning anything y. So y is a free variable, whereas x is the bound variable. X is the bound variable. And of course, we are going to consider, then this is the way that we are going to identify what are the free and what are the bounded variables. Bounded variables. Now, let us consider the other inference theory for predicate calculus. So here there are two rules will be there: rule of specification and rule of generalization. Rule of generalization. So here, rule of specification is US, that means universal specification. Universal specification. Whenever it is true, universal specification. This is rule US means universal specification. Rule ES means extension specification. And rule of generalization. Then we are going to take a E of G, existential generalization. Then U of G, we are taking it as a universal generalization. So what is the description of these rules? So here, the universal specification concludes from, for every x, A of x is true. For every x, A of x is true. Then it is also true for a particular value, particular variable, y. So this is universal specification. If the predicate is true for all the predicate point function is true for all the values of x, then automatically it is true for some particular value of x, that is we are taking it as y. And next another one is existence specification. So here it is from there exists x, A of x. There exists x, A of x. That means at least one x, A of x is true, then that x we are taking it as y. So here y is not a free variable, y is not a free variable. So because we are just giving a particular value to the x, so we are going to consider it as a y. Now existing generalization. So here it is A of x. So it is going to be true. If it is going to be true for one particular value, then we are going to write it as there exists y. There exists y means at least one y, at least one value A is going to be true. A is going to be satisfies that. So we are going to take it as there exists y, A of y. Universal generalization. So this concludes if it is true for x, then it is, that means while we are going to prove that it is not possible to prove all values of x, and we are going to take one particular value of x, then we are going to say that. We are going to generalize in the similar manner. If you are going to take x different values, x to different values, then it is automatically is also going to be true. That is going to be universal generalization. Let us consider now, show that there exists x, m of x follows logically from the premises for every x h of x, if h of x, then m of x, and there exists x, h of x. So from these two, there exists x, m of x is going to be true. Now, let us, which is similar to the earlier methods. So now we are going to consider, this is the first given premise. First given premises. That means whatever the earlier methods will be there. Those methods we are going to be adapted, and the same methods we are going to apply to the predicates, Now, we are going to consider the premises. This is one premises and this is another premises. So, this premises will be their given premises. This is the given premises. So, there exists x, h of x, means it is true if I am taking x is equals to y. X is equals to y. That means we are going to go for a existential, because we are going to use existential quantifier. So, we are going to say that existential specification. Now, another given premise, let us say, for every x, h of x. If h of x, then m of x is the given. So, for every means for all. So, we are going to take a particular value, that is y. So, this is a universal specification. Okay. So, this is true for all values, and this is only for a particular value we are going to consider. Then, automatically, from this and from this. So, h of y and h of y, then m of y. Using modus tollens, then we are going to get m of y. We know already that p, if p is true, then p to q is true. Then automatically q is also true. By using that, so here we are going to say that h of y is true, h of y to m of y is true, automatically m of y is true. So now, this is, we are going to apply two cases. One is existential specification and universal specification. We are going to apply both. So we are going to get a existential specification. Then we are going to generalize this existential specification. For that, we are taking there exists x, m of x. So this is nothing but the given thing. So there exists x, m of x. Now, let us consider the second example. Prove that there exists x, p of x and q of x, which is equals to there exists x, p of x, and there exists x, q of x. So now, this is the given. Left hand side, just we are going to take this as the given premise. Then we are going to particular that this is the existential specification. If you want to take it as y also, no problem. This is y and this is y. Let us say, because we have to show the difference between here and here. At least one, it is true for at least one, that one is a y we are taking. Then, so this is p of y and q of y. So, this is a conjunctive. This is a rule of disjunctive. P and q is true. Then automatically p is true as well as q is true. So for that reason we are going to get p of y and q of y. Both are true. Then this is an existential specification we are going to use, and we are going to generalize this, the existential specification. So there's we are going to existential generalization. So there exists x, p of x for this, and for this there exists x, q of x, and I'm just combining both. So p of x and q of x is also true. So which is nothing but p of x and q of x is true. This is the whenever if it is p is true and q is true, automatically P and Q is also true. Now let us consider the other problem. Show that for every x, P of x, if P of x, then Q of x, and for every x, Q of x, then R of x implies for every x, P of x, then R of x. So here and here these are the two given premises. From the two given premises we are going to get this. So here it is given. So here for all will there. So I am going to take a particular value. So we are going to apply universal specification. So here also for every will be there. So this is the given. So one particular value. So universal specification. So this is just we are going to take which is of the form P to Q and Q to R. Therefore both are true. Then automatically P to R is also true. So applying that formula, this is a hypothetical syllogism. Then we are going to get, P of x to R of x. Just combining these two, Q of y to P of just what is that? P of y to Q of y to R of y. So combining these two, not these two. So just combining these two, then I am going to get this. So rule of syllogism. So just applying rule 4, 5 and 2 and then it is 4. 2 and 4. And next whatever we are getting the result. So these two are universal specifications will be there. So now we are going to apply universal generalization. So for that reason, for every x I can. So this is the way that we are going to finding this. And another one is, let us consider the next one is statement with more than one variable. Earlier we consider a statement of a single variable. Now we have to consider a statement of two variables. Two or more than two variables. Let us consider this is, I'm just taking this is one and this is another predicate. Let us say here x and y. In the first one is x, y are two variables. Here x, y, z are three variables. Now, if these are the open statement containing 2 and 3 variables. So whenever if you are going to give a specific values to the variables which are there in the open statements, then this will become a proportions. And each and every proportion will have a truth value. Suppose for that let us consider x is equals to some number. Let us say x is equals to 5 and y is equals to 2, y is equals to 3. If I am going to consider this is y and this is x if I am taking, then if I am going to substitute in the expression, we are going to get it is a 5 plus 6 which is 11. So it is which is 11. This is nothing but a positive integer. So automatically we can say that truth value is true. Similarly, for x and y, z, if you are going to give some numbers, and we have to verify the sum is whether if it equals to 0, I can write it as a true. Otherwise, I can write it as a false. So this is we are going to represent. Suppose if I am going to consider a open statement with two variables, then we have to consider P of x comma y, Q of x comma y, or R of x comma y, like that. And if it is a three variables, then we are going to represent P of x comma y comma z, Q of x comma y comma z, and so on. So now similarly, there is a open statement. So P and Q are two open statements. Then or else I'm just considering this is equal to this and this is equals to this. Now, if I'm just giving some specific values to x and y, so x is 2, y is 4, y is 4, just substitute, that is x is equals to 2, 2 square, which is greater than or equals to 4. So 4 is greater than or equals to 4. So then it is true. So the truth value is true, which is true. So determine the truth value is the true. This is the true. Now 1 comma pi q. What is the q of x comma y is this? Q of 1 comma pi is x is equal to 1 and y is equal to pi, which is equals to 1 plus 2 is less than pi is nothing but 22 by 7. So 3 is less than 22 by 7, which is true. Which is true. So I am going to say this is the truth value is true. And like that, if I am just to substitute, this is x is equals to minus 3. So it is 9. 9 is greater than. So which is true? The first one is true. And the second one is 1 comma 3. So x is equals to 1. Y is equals to 3. 1 plus 3. 1 plus 2 is automatically 3. 3 is less than 3, which is false. So true and false, which will give a false. So like that, we can just specify. The particular values to the variables which are there in the open statements. Then we can get the prepositions. That is nothing but those preposition values, either it may be true or false. Now the quantified statement, more than one variable. Till now it's quantifieds we are going to use only for one variable. Now we are going to use for two variables. Suppose if I am going to take an open statement, or else I can call it as a predicate of two variables. Okay, p of x comma y. P of x comma y is an open statement. Then the possible ways I am going to represent x and y by using the quantifieds as for all x, for every x and y, I can use, or else there exists x, there exists y I can use, and for every x, there exists y I can use, and there exists x, and for every y. So these are the possible ways that I can assign the quantifiers to the variables which are there in the open statements. Okay, now let us consider, write down the following statements in the symbolic form. See now, every real number has an additive inverse. Every real number has an additive inverse. So here, the same statement I am going to write. Given any real number x, then there is a real number y such that x plus y or y plus x is equal to 0. So here for any, suppose if I am going to consider 1, what is a additive inverse is minus 1. Additive inverse is minus 1. So if I am taking additive inverses exist only 1. Not many. So if I am taking 2 is any real number if I am going to consider 2, then additive inverse is minus 2 is only 1. So here what I am going to take, for every x, okay, any x if I am going to consider, there will be at least one in such a way that x plus y, y plus x equals to 0. So this is the symbolic statement. For every x, there should be some y or at least y, one y or one y in such a which satisfies the property that x plus y is equal to y plus x is equal to 0. Then the second one is the set of real numbers has a multiplicative identity. So that means a multiplicative identity. If I am taking x, then there exists another y which is 1 by x. And if I am going to multiply, what we are going to call it, multiplicative identity, that means which is 1 1. So for every there exists x such that xy, yx, xy, yx. If I am taking y, then the multiplicative identity x. Multiplicative identity x. So multiplicative identity means if you are going to multiply that element with the multiplicative identity, that element alone we are going to get. So here x is the multiplicative identity. X is the multiplicative identity. Y is the element. If I am going to multiply with the multiplicative identity, the resultant will be y alone. The resultant will be y alone. So the multiplicative identity should be 1. Of course, sometimes 1. And this is for every y. So there exists x for every y. X into y is equals to y into x is equals to y. Is equals to y. Now let us consider the other one. So in the same way we are going to write there exist determine the truth values. There exists x, there exists y, xy is equals to 1. Xy is equals to 1. So there exists 1 means x means 1 we are going to take, 1 value. So let us consider x is equal to 1, y is equal to 1. So the product will become 1. So there exists. It is true. If I am taking not for all x I cannot consider for all y. So it is true for this. So the truth value is true. And the next for there exists x for every y, xy is equals to 1. Just similarly, see here, this is false. See, it is specified y, xy is equal to 1. So for every y it is not true. So if I am taking y is equal to 2, then 2 into 1 I am not getting 1. So this is obviously false. So similarly, there exists x, there exists y. 2x plus y is equal to 5 and x minus 3y is equal to minus 8. So if I am taking say a particular value which satisfies this. So both, but is a particular value which satisfies both. So if it is exists, then I can say that it is true. Otherwise, I can call it as false. So here, there is no x and y's which are satisfying both equations. So that solution does not exist. So this is a false. Like that we have to do. Then similarly, the negations we are going to calculate. So once if you are going to calculate the negation of for every means there exists. Negation of this. And negation of for every means there exists. There exists for every means there exists negation. Let us say there exists negation of there exists x, which is equals to for every x. Negation of for every x is equals to, which is similar to the single variable. So which is there exists x. And of course already we intimated in the earlier sessions while you are going to convert into a negation. So first of all we have to write this as of this form, negation of p rq, then apply the negation. So then it is a p and negation q. P is same as it is, no problem as it is, and will be there. Negation of this is greater than will be there, less than or equal to. So similarly, just wherever the conditional will be there, then we are going to convert it into the equivalent form. Then afterwards we are going to take the negation. So here there exists x, there exists y. Once again the same thing. This will not be changed. So this is same as it is, and then we have to consider the negation of this. So x is z is greater than or equal to x. So opposite z is less than or equal to x. Or then I am going to get like this. So this is whenever any conditional will be there, then we have to take its equivalent form. Then we are going to apply the negation. And we are going to find its equivalent forms by using this one. So with this, the mathematical logic, the first module of the third semester CSC students of IARE, which is going to be completed. So here I used the textbooks. One is a Tremblay and Manohar, okay, discrete mathematical structures, and another one is Dr. D.S. Chandrasekharaya, Prism's publication. These textbooks I used for my reference sake. And whatever the data I collected or I gathered from these two textbooks or some other textbooks I collected, and I represented all the things before you. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.